to be fair. Like he didn't just not show up. He like put in and they didn't get sub coverage for him.
That's really funny. Remember when that used to happen in chemistry and we'd all just sit there as long as possible before we Yep. That happened like every day. It happened once when we had a fire drill and then the bio teacher was like, "Where's your teacher?" And we were like, she was like, "It's been 45 minutes." And we're like, yeah. Then
It's a series of the form. So we're now going to look at series. We're going to shift from series of numbers to basically series as a function. And like the whole, what you work up to in this section is that you can you can estimate functions using infinite series. And we start that with a power series. And a power series is a series of this form where c sub n are coefficients, x is your variable. And so if we look at this infinite series, where it's c0, c1x, c2x squared, c3x cubed, it kind of resembles a polynomial, but it's a polynomial with infinitely many terms. And depending on the value of x, this series could converge or diverge. More specifically, this series is a geometric series. So this is if we let all Cn equal 1. And it becomes the geometric series x to the n. And if x is between -1 and +1, then that series will converge. And if x is bigger than 1 or less than -1, it'll diverge. And then more generally, if you shift the series, so if you subtract a, we call that a power series centered at a. And the reason we call it centered at a is, do you guys remember like conic sections? Like, for example, a circle centered at the origin will look like this: x squared plus y squared equals r squared. But if you want to shift that circle, it's x minus h squared plus y minus k squared. And that'll shift it to hk. So same idea here. If you just subtract a constant for all terms, that kind of shifts the power series. And so that's why we call it a power series centered at A. All right, and what we're going to look at is a few different power series. We're going to decide if they converge or diverge. All right, so let's go ahead and look at this specific power series. So sigma n factorial x to the n, and I want to know for what values of x is the series convergent. So basically what we're finding is the domain of this function, meaning the values of x that would make it converge. All right, and so now we have a few tests under our belt that will help us to decide on convergence or divergence. And so I'll remind you of the last one we learned was the ratio test. So I'm going to let a sub n equal the corresponding series sequence n factorial x to the n. And then I want to look at a sub n plus 1 over a sub n. And then we're going to let that approach infinity. All right. So we end up with n plus 1 factorial x to the n plus 1 over n factorial x to the n. So we want to simplify this. Do you remember the trick to get rid of the factorials? Remember that 4 factorial is 4 times 3 times 2 times 1. but it's also 4 times 3 factorial, right? So n plus 1 factorial is n plus 1 times n factorial. And I can rewrite x to the n plus 1 as x to the n times x. And so then I have over n factorial x to the n. I can get rid of my n factorial. I can get rid of x to the n. And then what I'm left with, and I actually do need absolute values here because x is a variable, so it's not necessarily positive. So then what I end up with is absolute value of n plus 1 times x. All right, and what we're looking at is letting n approach infinity. And do you guys remember the rule for the ratio test? If it's less than 1, it's convergent. If it's greater than 1, it's divergent, right? But here we're letting n approach infinity, so this is going to approach infinity, right? So the whole thing will approach infinity unless x is 0, basically. So it's only convergent when x equals 0, and it's divergent otherwise. Sorry. Okay. Same idea. For what values of x does this one converge? So this is a power series centered about 3. So again, this is a good candidate for the ratio test. So I'm going to let an be x minus 3 to the n over n. And now we're going to do a sub n plus 1 over a sub n. And I'm going to get x minus 3 to the n plus 1 over n plus 1 divided by x minus 3 to the n over n, absolute value. All right, so we end up with x minus 3 to the n times x minus 3 over n plus 1. I'm going to flip the denominator and multiply, so times n over x minus 3 to the n. All right, we can cancel the x minus 3 to the n's. And then we have absolute value of x minus 3 times n over n plus 1. I only need the absolute value around x minus 3 because the n's are all positive. We're going to be looking at the limit as n approaches infinity. So what I want to do here is divide numerator and denominator of this by n. Now I have x minus 3 times 1 over 1 plus 1 over n So now, if we look at the limit as n goes to infinity, the 1 over n is going to go to 0, and I'm just left with absolute value of x minus 3, right? And again, what do we need this ratio to come out to for the series to converge? So I'm going to set this less than 1. So absolute value of x minus 3 is less than 1. All right. And the way we deal with absolute values and inequalities is you set up the two situations. So drop the absolute value, x minus 3 is less than 1. And then you negate the right-hand side and flip the inequality. X minus 3 has to be greater than negative 1. Solve both of them. X is less than 4 and x is greater than 2. And so my interval of convergence is from 2 to 4. If x is between 2 and 4, it's convergent. All right, we're going to skip the third example. We're going to jump to the definition of radius of convergence. So there are three possibilities for convergence. One, the series converges only when x equals a. We saw that in our first example. Two, the series converges for all values of x. Or three, there's a positive number r that the series converges if x minus a is less than r and diverges if x minus a is greater than r. And that value r is called the radius of convergence. So in the last example we did, the radius of convergence was 1. Because we had x minus 3, absolute value of x minus 3 needed to be less than 1. All right, let's just do one more. Here we go. Find the radius of convergence and interval of convergence of the series. So just to remind you, to put it in context, let's go back to that last example. This is the interval of convergence. This is the radius of convergence. All right, we're going to hit this with the ratio test once again. So my a sub n is negative 3 to the n x to the n over root n plus 1. So if I look at the absolute value of a to the a sub n plus 1 over a sub n, the absolute value is going to get rid of that alternating part, so it'll just eliminate that negative, basically. Oh no, you know what? It won't, because look. All right, let's write this out. So it'll go. So we would have negative 3 to the n plus 1, x to the n plus 1 over basically root n plus 2. And rather than write this as division, I'm going to immediately flip and multiply. So then I'd have root n plus 1 over negative 3 to the n x to the n. Okay. So then this is now negative 3 to the n times negative 3 times x to the n times x over negative 3 to the n times x to the n. And then I still have that root n plus 2 down here, and I have the root n plus 1 up here. All right, so what can we get rid of here? We can get rid of the negative 3's to the n. We can get rid of x to the n. And so what we end up with is absolute value negative 3x. And I can write that all under 1 square root, root n plus 1 over n plus 2, right? All right, so this is positive 3 once I take the absolute value. So this is positive 3, absolute value x, root n plus 1 over n plus 2. All right, under that square root, let's divide by n, both numerator and denominator, and then we'll evaluate the limit as n goes to infinity. So I have 3 absolute value x. This is going to become root 1 plus 1 over n over 1 plus 2 over n. So I just divided numerator and denominator by n. So the square root just becomes 1 because these both go to 0. So we have root 1 over root 1, which is just 1. And so this all evaluates just to 3 times the absolute value of x, which for this to converge, we need that ratio to come out to, once again, less than 1, right? So go ahead and divide by 3. Absolute value of x needs to be less than 1/3. There's our radius of convergence. So the radius of convergence is 1/3. The interval of convergence is just solving that inequality. And when you solve that inequality, you're going to get x needs to be between negative and positive 1/3. That's it. All right, so there is a problem set. This will be your last problem set, and we'll call it a year.